Hello, my name is Peter Kamawungai and I'll be presenting my project, which is on hybrid maximum power point tracking technique for partial and non-partial shading conditions. Aims and objectives. The aim of this project is to develop an optimal hybrid maximum power point tracker for both partial and non-partial shading conditions. The objective is to develop a hybrid maximum power point tracking algorithm for partial shading conditions, to construct the hybrid maximum power point tracker system using MATLAB Simulink, and to evaluate the performance of the constructed system via simulation.
Hello, my name is Peter, and as mentioned, my project involved the building of a hybrid maximum power point tracker using MATLAB Simulink, and I was able to build a hybrid slime mode algorithm hybridized with perturb and observe maximum power point tracker as seen in front of you. The design system was designed in MATLAB Simulink and consisted of four main components. The first component is the PV array, which consists of four PV modules connected in series together with bypass diodes. This is the irradiance value of the PV module, and this is the solar cell temperature. So as currently seen, the setting is 500, 800, 1000, 1000. This symbolizes a partial shading pattern as the irradiance values are not all equal in each PV module. So the first simulation we'll be running will be the partial shading condition. Next, we have the maximum power point controller, which consists of a signal conditioning block, a SIMOD-based algorithm code that is able to enable the global maximum point tracking, a pulse wave modulator that is able to generate the duty cycle of the system. Finally, next we have the boost converter circuit, which consists of input capacitance, a MOSFET diode, and an inductor, and an output capacitance. Finally, we have the graphical tracking function block, which enables us as a user to visually see the tracking of the system as it tracks the maximum power point. So I'll go ahead and run the system as I explain more about it. And first thing we can be able to see is the graphical figure block come up. And with this block, we're able to see visually the tracking of the maximum power point of the system as seen here. And once the system tracks the maximum power point, the ball will be able to settle at that particular point. And while it goes on, I will explain more about the system. And as mentioned before, this system consists of a PV array, which is connected in series to a boost converter circuit, and the boost converter circuit has an output voltage that is regulated by a duty cycle of the MOSFET diode. The maximum power point controller is used to extract the maximum power from the PV array and measures the current and voltage of the PV panel, thereby generating a duty cycle. This generated duty cycle is given to the driver circuit, which generates a pulse wave module for controlling the switching of the MOSFET. The main function of this maximum power point tracking algorithm is to develop an effective tracking algorithm that can be able to be used in practical PV systems whereby harvested power is under changing insolation or under changing weather patterns. To develop this maximum power point tracker, we're able to overcome limitations of conventional techniques such as perturb and observe, which have limitations as low tracking efficiency, steady state oscillations, and various transients. And to implement the above maximum power point tracking controller algorithm is a real addition to the world photovoltaic system. So as we can see, the system is still tracking the maximum power point, and the main output of the system is the output power, which we're going to be able to see here. And through this scope, finally, once the system tracks the maximum power, it's going to be able to level off at the maximum power. The other main output is the duty cycle of the system, which can be seen through this scope. And The system works with implementing the slime mold algorithm initially to track the global maximum power point, and then after, as we can see through the representation of this point, pattern observe is now activated to locate the local peak of the maximum power point. Once the system is done simulating, we're going to be able to have a steady duty cycle as well as flattened output power, and these are the main outputs of the system. So for the given setting, which is partial shading setting, the system is going to be able to settle at the maximum power point soon. The system roughly takes 5 minutes to locate the maximum power point. And just to provide a working principle, as mentioned, the system consists of two hybridized techniques, which is a perturb and observe that tracks the maximum power point by perturbing the operating point, then observing the difference between the power in the perturbations. After observing the power, it calculates the PV array's power by measuring the voltage and current, and this provides a perturbation in the duty cycle based on the variation of power. The perturb and observe is activated, as mentioned, after the slime mold and is able to locate the local peak. So a summary of the system is that it works through the two techniques. The initial one is the slime mold in locating the global maximum peak. And finally, the perturb observe is activated to locate the local peak, thereby enabling the maximum power point tracking in partial shading condition. When we come to the PV array and set a uniform or non-partial shading pattern, which can, for example, can be 500, 500, 500, 500, that will symbolize a non-partial shading pattern, and the same results can be observed in the output power scope and in the duty cycle scope, where we'll be able to see the tracking of the maximum power point. Also in the figure block as seen, we can now see that the global maximum power point has been located. So now the perturb and observe has been activated and is now locating the local peak of the system. And this is a visual representation of the perturbation over an operating point as it tries to locate the local peak. And once the system will be done, we'll be able to have a steady duty cycle and a steady output power value. And that is basically the system. Thank you for listening to my presentation. I'm Peter Mungai. Here, as we can see, steady output power and steady duty cycle. If there's any questions, kindly ask and I'll be happy to answer. Thank you.